opposite to d1 f1. So negative sign. This is equation 2. Normally the anti-clockwise or clockwise movements are taken as to be positive or negative. Means anti-clockwise are taken positive and clockwise are taken negative. So check here. So f1 d1, this is anti-clockwise, and f2 d2, this is clockwise. So clockwise are negative, anti-clockwise are positive. So we can write d1 f1 minus d2 f2. Note R reacts at fulcrum itself and has zero moment about the fulcrum. So R has zero moments about the fulcrum. In the case of lever, force F1 is usually some weight to be lifted. It is called load. And the distance from the fulcrum d1 is called load arm. Force F2 is the effort applied to the lift the load. Distance d2 of the effort from the fulcrum is the effort arm. Equation 2 can be written as d1 f1 d2 is equal to d2 f2, or load arm into load is equal to effort arm into effort. The above equation expresses the principle of moments for a lever. Incidentally, the ratio f1 slash f2 is called mechanical advantage. So mechanical advantage is equal to f1 by f2 is equal to d2 by d1. So how this came? This came from this equation. So we can write d1 f1 is equal to d2 f2. Now f1, and from f2 this came this side, so it is upon this side, it is multiplied, so this side it came upon, and d2 left here, and from d1 it went here. So this is the ratio we are talking about. This is called mechanical advantage, which is represented in equation 7.32. So if the effort arm d2 is larger than if the effort arm d2 is larger than the load arm, the mechanical advantage is greater than 1. So if d2 is greater than d1, then mechanical advantage. So if d2 is greater than d1, then mechanical advantage is greater than 1. Mechanical advantage is greater than 1. Why? Because put the values. If d2, say for example, if d2 is 2 and d1, if d2 is 2 by 2 d1, for example, say if d2 is 2 d1, so mechanical advantage say will be d2 by d1. Instead of d2 we can write 2 d1 by d1 cancel. So mechanical advantage in this case is greater than 1 because mechanical advantage is 2 here, is 2. So at any point in time, if d2 is greater than, that means the effort arm is greater than the load arm, then the mechanical advantage will be greater than 1. This is very important for the objective questions, for neet and other exams. Mechanical advantage greater than 1 means that a small effort can be used to lift a large load. So what is the meaning? Physical meaning is that with less effort, big or large load can be lifted. There are several examples of a lever around you beside the seesaw. The beam of the balance is a lever. Try to find out more such examples and identify the fulcrum. The effort arm and load arm of the lever in each case. You may easily show the principle of moment holds even when the parallel forces F1 and F2 are not perpendicular but acts at the same angle to the lever. Now let us study about center of gravity. Many of you may have the experience of balancing your notebook on the tip of a finger. Figure 7.24 illustrates the similar experiment that you can easily perform. Take an irregular shaped cardboard and a narrow tipped object like a pencil. You can locate by trial and error a point G on the cardboard where it can be balanced on the tip of a pencil. The cardboard remains horizontal in this position. This point of balance is the center of gravity, CG, of the cardboard. The tip of the pencil provides a vertically upward force due to which the cardboard is in mechanical equilibrium, as shown in the figure 7.24. So let us see the figure 7.24. Here is the 7.24 figure. So balancing the cardboard on the tip of a pencil, the point of support G is the center of gravity. So this is the pencil and this is the point G which supports the cardboard. So this side the weight is equal to m1g, this side the weight is m2g and the reaction is acting upward. So this is acting downward, this is acting downward, the reaction is acting upward. Now the, the reaction as shown in the figure 7.24, the reaction of the tip is equal and opposite to mg. The total weight of, that is the force of gravity on the cardboard, and hence the cardboard is in translational equilibrium. It is also in rotational equilibrium. If it were not so, due to unbalanced torque, it would tilt and fall. There are torques on the cardboard due to the force of gravity like m1g, m2g, etc., acting on the individual particle that makes up the cardboard. Now the CG of the cardboard is so located that the total torque on it due to the force m1g and m2g etc. is 0. If r1 is the position vector of ith particle, Ri is the position vector of ith particle of an extended body with respect to its CG, then the torque about the CG due to the force on the of gravity on the particle T1 is equal to R1 M1 Ti is equal to Ri multiplied by M1 Mi the total gravitational torque about Cz is 0. So remember the total gravitational torque about center of gravity is 0. So we can write R tau z is equal to sigma tau I, sigma which is equal to sigma Ri multiplied by miz which is equal to 0. Equation 7.33. We may therefore define Cz of a body as the point where the total gravitational torque is 0. This is very important. From this equation we have found the definition of Cg, the center of gravity. So what is center of gravity? Center of gravity of a body is the point where the total gravitational torque on the body is 0. We notice that equilibrium as equation 7.33 G is the same for all the particle and hence it comes out of the summation. This gives since G is non-zero. Sigma mi is equal to 0. Remember that the position vector r is taken with respect to Cg. Now, in accordance with the reasoning given below, equation 7.4a in section 7.2, if the sum is 0. The origin must be the center of mass of the body. Thus, the center of gravity of the body coincides with the center of mass. We note that this is true because the body being small, g does not vary from one point of the body to other. If the body is extended, g varies from one part to part of the body. Then the center of gravity and the center of mass will not coincide. Basically, the two are different concepts. The center of mass has nothing to do with center of gravity. Remember this. It depends only on the distribution of mass of the body. Center of mass depends upon the distribution of the mass of the body. It has nothing to do with the center of gravity. In section 7.2, we found out the position of center of mass of several regular homogeneous objects. Obviously, the method used there gives us also the center of gravity of the body if they are small enough. Figure 7.25 illustrates another way to determine CG of a regular shaped body like a cardboard. Let us see figure 7.25. This is 7.25. So what they have done, they have uh, determined the center of gravity of a body of a irregular shape. The center of gravity G lies on the vertical AA dash through the point of suspension of the body A. So what we have done, we have hanged, suspended the body and through different points, and we have drawn a line, and the intersection of that line gives the center of gravity of the irregular shaped cardboard. So figure 7.25 illustrates another way to determine CZ of a irregular shape body like a cardboard. If we suspend the body from a point like A, a vertical line through A pass through CG. We mark the vertical line A1. We then suspend the body through other point B and C. The intersection of the verticals gives CG. Explain why the method works. Since the body is small enough, the method allows us to determine the center of mass. Now, let us do few numerical examples. A metal bar 70 centimeter long and 4 kg in mass, supported by two knife edge placed 10 centimeter from each end. A 6 kg weight is suspended at 30 centimeter from one end. Find the reaction at the knife edge. Assume the bar to be uniform cross section and homogeneous. So this is the figure according to the question. Now figure 7.26 shows the rod AB. This is the rod AB. The position of the knife edge K1 and K2. So two knife edge are K1 and K2. The center of gravity of the rod at G and suspended weight at P. At G and suspended weight at P. Suspended weight at P. Note the weight of the rod W acts at its center of gravity G. The rod is uniform in cross section and homogeneous. Hence, G is at the center of rod. AB is equal to 70 centimeter, AG is equal to 35 centimeter, AP is equal to 30 centimeter, PG is equal to 5 centimeter, AK1 is equal to BK2, that is 10 centimeter, and KG1 is equal to K1G is equal to K2G is equal to 25 centimeter. Also, W is equal to weight of the rod. So all the figures we have find that out given in the question. Now weight of the rod is 4 kg and W1 is the suspended weight, that is 6 kg. R1 and R2 are the normal reactions to support the knife edge. For translational equilibrium of the rod, we can write the reaction R1 plus R2 minus W1 minus W is equal to 0. All the upward force minus all the downward force is equal to 0 at translational equilibrium. This is all about equation number 1. Note W1 and W1 and W are acting vertically downward and R1 and R2 are acting vertically upward. For considering rotational equilibrium, we take moment of force a convenient point to take moments about is G. The moments of R2 and W1 are anticlockwise, therefore positive, whereas the moment of R1 is clockwise, whereas negative. So for rotational equilibrium, we can write R1 multiplied by K1G plus W1 multiplied by PG plus R2 multiplied by K2G is equal to 0. This is all about equation number 2. It gives that it is given that W is equal to 4 gram and uh, 4g Newton. W is equal to 4g Newton and W1 is equal to 6g Newton. where g is the acceleration due to gravity. We take g is equal to 9.8 meter per second square. With numerical value inserted from 1, r1 plus r2 minus 4g minus 6g is equal to 0, or r1 plus r2 is equal to 10g Newton, which is equal to 9.8 Newton. This is all about equation number 3. Now, from equation 2, we can write minus 0.25 R1 plus 0.05 W1 plus 20.25 R2 is equal to 0, or R2 minus R1 is equal to 1.5 1.2 gram G Newton, which is equal to 11.76 Newton. So this is all about equation number 4. Upon solving equation 3 and 4, we get the value of reaction R1 and R2. Thus the reaction of the support are about 55 Newton and 43 Newton. 55 Newton at K1 and 43 Newton at K2. Let us solve the next question. So before solving it, let us the two main points to solve this problem. First is find out the equation at translational equilibrium of the rod and find out the equation for rotational equilibrium. And all the downward force are acting downward, and all the weights are acting downward, and all the reactions are acting upward. And you have to take the anti-clockwise rotational motion as moments as negative and clockwise moment as positive. Anti-clockwise moment as positive and clockwise moment as negative. And after solving the equation, these two equations, translational and rotational equilibrium, then we can easily find out the values. Now next, example 7.9. A 3-meter long ladder weighing 20 kg lean on a frictionless wall. Its feet rest on a floor 1 meter from the wall as shown in the figure 7.27. Find the reaction force of the wall and the floor. So this is the ladder, this is the figure shown, and this is the vertical wall. This is 1 meter away from the vertical wall, and all the given values in the problem are drawn in the figure. Now the ladder AB is 3 meter long, so we have drawn AB as 3 meter. Its foot A is at a distance AC is equal to 1 meter, so this is 1 meter. Already we have drawn it from the wall. From Pythagoras theorem, BC is equal to 2 root 2. The force on the ladder are its weight acting at its center of gravity D, reaction force F1 and F2 of the wall and the floor respectively. So weight is acting vertically downward here from this through the center of gravity. F1 and F2 are acting this side. So this is F1 and F2 are acting here. Now let us see F1 and F2 on the wall and the floor respectively. Force F1 is perpendicular to the wall since the wall is frictionless. Force F2 is resolved into two components, the normal reaction and the force of friction, F. Note that F prevents the ladder from sliding away from the wall and is therefore directed towards the wall. For the translational equilibrium, taking the force in the vertical direction, N minus W is equal to 0. Take, taking the force in the horizontal direction, F minus F1 is equal to 0. The rotational equilibrium, taking the moments of force about A. So take the moment of force about A and take the rotational moment equilibrium at rotational equilibrium, it is this. And just we found the value of weight. From equation 1 we can find out the since weight is equal to n, w is equal to n, therefore n's value is also the same. Putting this value in from equation 3 we can find out the value of f1, and from 2 we can find out the value of f, and angle we can find out if tan alpha is equal to n by f, therefore we know n and f, so we can find the value of alpha, that is 80 degree. Now moment of inertia. We have already mentioned that we are developing the study of rotational motion parallel to the study of translational motion with which we are familiar. We have yet to answer one major question in this connection. What is the analog of mass of rotational motion? We shall attempt to answer this question in the present section. To keep this discussion simple, we shall consider rotation about a fixed axis only. Let us try to get expansion for the kinetic energy of rotating body. We know that for a body rotating about a fixed axis, each particle of the body moves in a circle with linear velocity given by equation 7.19 referred to figure 7.16 for a particle at a distance from the axis. Linear velocity is v I is equal to r omega. The kinetic energy of the motion of the particle Ki is equal to half mi v I square is equal to half mi instead of vi we will put ri omega, therefore it will be half mi uh, ri square omega square, where mi is the mass of the particle. The total kinetic energy K of the body is then given by the sum of the kinetic energy of the individual particles. So K is equal to, we can write sigma I is equal to 1 to n, and Ki is equal to half I is equal to 1 till n, and in bracket mi ri square ri square omega square. Here n is the number of particles in the body. Note omega is the same for all particles. Hence, taking omega out of the sum, we get k is equal to half omega square, sigma I is equal to 1 to n mi ri square. We define a new parameter characterizing the rigid body called the moment of inertia. I is given as I is equal to capital I is equal to sigma small I is equal to 1 to n mi ri square, which is represented by equation 7.34. With the definition, we can write k is equal to half I omega square. So half MIRI square instead here. If we put half MIRI square as I, then it will whole become I omega square. So kinetic energy is equal to half I omega square. Note that the parameter I is independent of magnitude of angular velocity. It is the characteristic of a rigid body and the axis about it which it rotates. Compare equation 7.35 for the kinetic energy of rotating body which with the expression for the kinetic energy of a body in linear or translational motion. K is equal to half mv square. Here m is the mass of the body and v is its velocity. We have already noted the analogy between the angular velocity omega in respect to the rotational motion about a fixed axis and linear velocity v in respect to the linear motion. It is then evident that the parameter moment of inertia I is the desired rotational analog of mass. In rotation about a fixed axis, the moment of inertia plays a similar role as mass does in linear momentum. So, what is moment of inertia? Basically, if we want to understand, so moment of inertia plays the same role as mass plays in the linear momentum. Moment of inertia plays the same role in rotational momentum, in rotational motion. We now apply the definition equation 7.34 to calculate the moment of inertia in two simple cases. Consider a thin ring of radius r and mass m rotating about its own axis around its center and angular velocity omega. Each mass element of the ring is at distance r from the axis and moves with a speed r omega. The kinetic energy is therefore K is equal to half mv square, which is equal to half m r square omega square. Instead of v we have written r omega, so half m r square omega square. Comparing with equation 7.35, we get I is equal to m r square. So we can write here thus the thus if we put mr square as I, then it will be equal to, so in equation 7.35 it is K is equal to half I omega square. Then compare this to half I omega square and half mr square omega square. So both are kinetic energy, so we can write I omega square is equal to half m r square omega square. So we can write here as, now compare these values. Say if you cancel it also, then also we can write I is equal to what is left m r square. So that is only written here, I is equal to m r square. So moment of inertia of a ring is this much. Now take a rigid massless rod of length L with a pair of small masses rotating about an axis through the center of mass perpendicular to the rod, shown in the figure 7.28. So this is the figure. So m by 2 masses, L by 2 um, distance, this distance and this distance. So it is passing through the center of mass and it is rotating. Now each mass m by 2 is at a distance L by 2 from the axis. The moment of inertia of the masses is therefore m by 2 L mr square. So what we can write, m by 2 is m and r is L by 2 square plus m by 2 multiplied by r square is L by 2 square. Thus, the pair of masses rotating about the axis through the center of mass is perpendicular to the rod. So, if you add it, then what you will get, ml square by 4. I is equal to ml square by 4. Table 7.1 gives the moment of inertia of various familiar regular shaped solids about specific axis. As the mass of the body resides, we'll see the table 7.1 afterwards. Let us first complete this part. As the mass of the body resists a change in its state of linear motion, it is a measure of its inertia in linear motion. Similarly, as the moment of inertia about a given axis of rotation resists a change in its rotational motion, it can be regarded as a measure of rotational inertia of the body. It is a measure of way in which different parts of the body are distributed at different distance from the axis. Unlike mass of body, the moment of inertia is not fixed quantity but depends on the orientation and position of the axis of rotation with respect to the body as a whole. As a measure of the way in which mass of the rotating rigid body is distributed with respect to the axis of rotation, we can define a new parameter, the radius of gyration. It is related to the moment of inertia and the total mass of the body. Notice from the table of 7.1 that in all cases we can write I is equal to mk square, where k is the dimension of length for a rod about the perpendicular axis at the midpoint. K square is equal to L square upon 12, that is K square is equal to K is equal to L by 12. So K is equal to L by root 12. Similarly, K is equal to R by 2 for a circular disc about its diameter. The length K is the geometrical property of the body and the axis of rotation. It is called radius of gyration. The radius of gyration of a body is about an axis may be defined as the distance from the axis of a mass point whose mass is equal to mass of the whole body and whose moment of inertia is equal to moment of inertia of the whole body. So the radius of gyration of a body is about the axis may be defined as the distance from the axis of mass of a mass point whose mass is equal to mass of the whole body and moment of inertia and whose moment of inertia is equal to the moment of inertia of the whole body about the axis. Thus, moment of inertia of a rigid body depends upon the mass of the body, its shape and size, distribution of mass about the axis of rotation and position of orientation of the axis of rotation. From the definition equation 7.34 we infer that the dimension of moments of inertia ml square and SI unit is kg meter square. So this is important for objective questions. The dimension for moment of inertia dimension is ml square or ml2, ml to the power 2, and SI unit is kilogram kg meter square. The property of this extremely important quantity I as a measure of rotational inertia of a body has been put to a great practical use. The mechanics such as steam engine and the automobile engine etc. that produce rotational motion have the disk with a larger moment of inertia flywheel called a flywheel. Because of its large moment of inertia, the flywheel resists the sudden increase or decrease of the speed of the vehicle. It allows to gradual change in the speed and prevent jerky motion, thereby ensures a smooth ride for passengers on the vehicle. Theorem of perpendicular and parallel axis. These are two useful theorems relating to the moment of inertia. We shall first discuss the theorem of perpendicular axis and its simple yet ins instructive application in working out the moment of inertia of some regular shaped bodies. We'll discuss this table afterwards. Let us first do the theorem of perpendicular axis. This theorem is applicable to the bodies which are planar. In practice, this means the theorem applies to the flat bodies whose thickness is very small compared to the other dimensions. Example, length, breadth, or radius. Figure 7.29 illustrates the theorem. It states that the moment of inertia of a planar body or lamina about its axis perpendicular to the plane is equal to the sum of moment of inertia about the two perpendicular axes concurrent with the perpendicular axis and lying in a plane of the body. So let us see figure 7.29 first. Theorem of perpendicular axis applicable to the planar body x and y axis are the two perpendicular axes in the plane and z axis is perpendicular to the plane. Now, the figure shows that planar body, an axis perpendicular to the body through a point O is taken as the z-axis. The two mutually perpendicular axes lying in the plane of the body and concurrent to the z-axis that is passing through O are taken as x and y-axis in the theorems. The theorem states that Iz is equal to Ix plus Iy. This is equation 7.36. Let the let us look at the usefulness of the theorem through the example. What is the moment of inertia of a disk about one of its diameter? So we assume the moment of inertia of a disk about an axis perpendicular to it and through its center is known as mr square upon 2. where m is the mass of the disk and r is its radius. This value from where we got? From table 7.1. So now let us see 7.1. So we are taking the example of a disk. So this is the disk. The fourth number is applicable to us. So body is circular disk, radius r, perpendicular to disk at center. Moment of inertia is mr square upon 2. In this way, various shaped bodies are given and their moments of inertia are given in this table. This table is itself important. We have to remember this table because this moment of inertia of different bodies uh, can be asked in numericals. So directly we will put the values in the numerical and solve the numerical. So in our case, mr square by 2, where m is the mass of the disk and r is its radius. The disk can be considered to be planar body. Hence the theorem of perpendicular axis is applicable to it. As shown in figure 7.3, we take three concurrent axes through the center of disk. O as x, y, z axis, x and y axis lies in the plane of the disk and z is perpendicular to it. By the theorem, perpendicular axis iz is equal to ix plus iy. Now x and y axis are along two diameters of the disk, and by symmetry the moment of inertia of the disk is same about any diameter. Hence iz is equal to iy, iz is equal to 2 ix, and ix is equal to mr, ix is equal to iy, so iz is equal to 2 ix and iz is equal to mr square by 2. Therefore, ix is equal to iz by 2, which is equal to mr square by 4. Which is equal to mr square by 4. Thus, the moment of inertia of the disk about any diameter is mr square by 4. Find similarly the moment of inertia of a ring about any of its diameter. Will the theorem applicable in the solid cylinder? What is the moment of inertia of a disk about its diameter? So we have already done here. This is the moment of inertia. This is the mr square by 4. Now let us move forward. Theorem of parallel axis. This theorem is applicable to the body of any shape. It allows to find the moment of inertia of a body about any axis. Given the moment of inertia of a body about the parallel axis through the center of mass of a body, we shall only state the theorem and not give the proof. We shall, however, apply it to a few simple situations which will be enough to convince us about the usefulness of the theorem. The theorem may be started as follows. The moment of inertia of a body about any axis is equal to the sum of the moment of inertia of the body about the parallel axis passing through the center of mass and product of its mass and square of the distance between the two parallel axes. As shown in figure 7.31, Z and Z dash are the two parallel axes separated by a distance A. The Z axis passes through the center of mass A and rigid body of the rigid body. The then according to the theorem of parallel axis, Iz is equal to Iz dash is equal to Iz plus Ma square. So let us see the figure here. So we need to find the moment of inertia at a distance a from the line passing through the center of gravity. So the theorem of parallel axis, the z and z dash are the two axes parallel to two parallel axes separated by a distance a. O is the center of mass of the body. O dash is equal to a. So we have to find the center of moment of inertia through the parallel axis z dash. So z dash is equal to Iz plus Ma square, where Iz and Iz dash are the moment of inertia of the body about z and z dash axis respectively. M is the total mass of the body and A is the perpendicular distance between the parallel axes. Now let us see few of the numericals. What is the moment? Numerical example 7.11. What is the momentum? What is the moment of inertia of a rod of mass m, length l, about its axis perpendicular to it through one end? For a rod of mass m and length l, I is equal to m l square upon 12. Using the parallel axis theorem, I dash is equal to I plus ma square with a is equal to 1 by l by 2. We get I dash is equal to ml square by 12 plus ml square by ml by 2 whole square, that is ml square by 3. We can check this independently since I is half of the moment of inertia of the rod of mass to m and length to l about its midpoint. I dash is equal to 2m 4l square by 12 multiplied by half multiplied by l by 2, that is ml square by 3. So this is solved here, simple. So from where we got ml square by 12? From the table. From the table, if you see the moment of inertia of a rod, then you will get ml by 12. Yes, uh, thin rod, you see ml square by 12. So you have to mug up this of a thin rod of length l. So you have to mug up this moment of inertia of a solid bodies of uniform shape for solving the numericals. Now next example, what is the moment of inertia of a ring about a tangent to the circle of the ring? The tangent to the circle tangent to the ring in a plane of the ring is parallel to one of the diameter of the ring. The distance between these two parallel axes are r. The radius of the ring, r is the radius of the ring. Using the parallel axis theorem, so this is diameter, this is tangent, so I tangent is equal to I diameter plus mr square. This is the parallel axis theorem. So instead of I diameter, we'll write m r square by 2. From where we get this value? From the table. And plus this mr square, we have written mr square. So 3 by 2 mr square. 3 by 2 mr square. So let us skip today's class till here. So let us recapitulate what we have done in today's class. So we have started today with principle of moments. Yeah, we have started from here. We have done principle of moments, and where we have done load into load arm is equal to effort into effort arm, and derivations for mechanical advantage. Then we have done center of gravity, we have done the definition, we have done the explanation how to find the center of gravity. We have done few examples um, uh, for equilibrium. Then we have done moment of inertia. Then we have done the moment of inertia, radius of gyration, the concepts, the derivations. Then we have done two theorems, theorem of perpendicular and parallel axis. This moment of inertia, the chart, just we have seen the chart, so you have to mug up the chart to solve the numericals. We have done the theorems of perpendicular axis. We have also done the theorems of parallel axis and solve few of the numericals based on these theorems. So in the next class we'll start with kinematics of rotational motion about fixed axis. We request you, if you have not subscribed our channel, please subscribe it. Please like our videos and share among your friends and relatives. Please click on the bell icon to get automatic notification whenever a new video is uploaded by us, so that you will not miss any of the important videos or updates from us. Thank you for watching our channel and supporting us. Thank you very much.